Good evening, everyone. I hope I'm audible.
Good evening, ma'am. Yes, ma'am, you're audible.
Let's continue with what we left in the last class. So, there we had given a matrix space XD. Uh, we are going to construct its completion. So, we start with fixing X naught. And for every X in X, we define a function fx from X to R. We had seen earlier in the previous session that fx is bounded, then this is for every x. Fx is continuous, and then we have the map f from x to bcxr is an isometric let x star equals to fx closure, so that x star is a complete matrix space that contains an isometric image of X. Now, since F is an isometry, so Fx is an isometric image of X. And Fx is clearly a subset of Fx closure, which is equal to X star. This implies X star image of X. Next, we need to show that this X star is complete matrix space. For that, we can directly use the fact that Fx closure of any set is always closed. This is a closed subset of the matrix space BCXR, which is a complete space. We know that this is complete. The closed subset of a complete space is again a complete space. This implies X star equals to Fx bar is complete. Hence, X star is a complete matrix space that contains an isometric image of X. Next, part 4. Now let Y be a complete matrix space that contains an isometric image of X. So that we can find an isometry from X star to Y. Such that a point that corresponds to X in X star gets mapped to a point that corresponds to X in Y. Now let's firstly see what this question is trying to say. So we have a complete matrix space Y, the complete matrix space, and it contains an isometric image of X. That means there exists an isometry, say G from X to Y. Clearly, Gx is a subset of Y. So that means Y contains an isometry image of X. So yes, we have this is an isometry. Okay. Then we need to show that there exists some other isometry, say I. We need to show that we can find an isometry from X star to Y. X star to Y such that a point that corresponds to X star. So suppose um, we had fx in X star. Obviously, X star contains all elements of this form or limit of sequence of functions in this form. So if fx is in X star and y is equal to g of this X, then we should have X in star gets mapped to a point that corresponds to X and Y. So that means I of fx should be equal to Y or gx. I hope this is clear. What we want to show? We want to show that there exists an isometry from X star to Y such that a point that corresponds to X and X star, basically X star was containing an isometric image of X. So any point X in X, this is mapped to some fx and this is an X star. Now this fx, which was a function of this form, should be mapped to a point that corresponds to X and Y. That means that corresponds to some X mapped in Y. So this should be equal to Y, where Y is equal to gx. So I'll give you some idea about the proof. I want you to do the proof in detail. So I'll just give an idea. Dimension. So basically, we need to find such an isometry. This should be an isometry. So we have x star is equal to fx closure, which is fx union fx prime, the set of all limit points of fx. Now, for any fx and fx, clearly there exists some x and x such that fx is equal to fx. We define I for this x, for this fx. We define I at this fx to be equal to g of x. Then we need to define I for the points or the function in fx prime or fx bar minus fx. And for f belonging to fx prime, or in fact, right, fx bar minus fx. This implies now, since clearly this is a limit point because it is lying in closure and not an element of f and not an element of the set fx, that means it is clearly a limit point. That means there exists a sequence. There exists a sequence fn of obviously distinct points in fx such that these fn converges to f, and this convergence is in the space bcxr. Now, since each fn is in fx, this implies there exists xn in x such that fn is actually equal to fxn for every n in n. This implies fxn converges to f in bcxr. So we need to define I on this f. So I define I at this f to be equal to limit n tending to infinity gxn. Therefore, I fx bar to y is defined as this is equal to gx if f is equal to fx. Otherwise, it is equal to limit. So in that case, we have this is equal to limit n tending to infinity gxn if f is equal to limit n tending to infinity fxn. Now I want you to see yourself, check that this I is an isometry. So basically this problem tells us that this implies that there exists a natural isometry because obviously this map was I haven't done anything new to define this map because I already had G. This Y was already given. Based on Y, we had G. Based on G, we constructed this isometry I. That means that's why we call it natural isometry. So this implies there exists a natural isometry from X star to any complete matrix space. Obviously, Y was any arbitrary complete matrix space, provided it contains an isometric image of X. Any complete matrix space that contains an isometric image of. So that was the relevance of this problem. I would like you to try further parts of this problem yourself. And if you have any doubt, please let me know. Then I'll solve only that part in next class. So yeah, let's discuss the example you asked me in last class related to the connectedness. Show that the set R2 minus Q2 is connected. So firstly, let's recall what do we mean by connected set, path connected set and all. Recall a matrix space X is said to be connected, or I'll start with the definition of disconnected, and whatever is not cannot be disconnected, is connected. Is said to be disconnected if there exist two subsets A and B, subsets of X, such that A closure intersection B is empty, B closure intersection A is empty, none of the sets are empty, and we can write X equals to A union B. So basically, if two sets satisfy this property that A closure intersection B is empty and B closure intersection A is empty, provided both the sets are non-empty, we say that both these sets are separated. A and B are separated. So if we can write a matrix space as union of two separated sets, then it is said to be a disconnected space. Else, it is called connected set. And if there does not exist any such A and B, we say X is connected. Next comes the path connected. So by path connected, we mean that for any 2 points in this set, we can ideal in layman language, you can say that we can construct a path that joins those 2 points. So that path is actually represented by a continuous map. We have path connected. A matrix space X is said to be path connected if for any x and y in X there exists a continuous map gamma rho 0 1 to X such that gamma 0 is X. That means at one end it is mapped to the point X, at the other end it is mapped to the point Y, and there exists a continuous line that joins those points. This map gamma is referred to as a path or curve. So this is a result that every path connected set is connected. So we will be using this result. So basically we'll show that R2 minus Q2 is path connected and hence connected. Solution. So all we need to do is construct a path that joins any arbitrary 2 points in R2 minus Q2. Every path connected space is connected in order to show that R2 minus Q2 is connected. So we claim that R2 minus Q2 is path connected. Now let X and Y be any two distinct points in the set. Suppose X is equal to R2 minus Q2. So suppose X not equal to Y be two distinct points in R2 minus Q2. Obviously, since there are two distinct points in R2 as well, so we can find two different circles, distinct non-intersecting circles, such that they have center at X and Y. That means let C1 and C2 be so you're saying in the definition, uh, why in definition disconnectedness, we use A closure intersection B and A intersection B closure. Instead, you want to say that instead of this, we write A closure intersection B closure to be empty. I think that won't work. Mm, I don't remember it clearly. See, right now I don't remember, but there is a reasoning for this. Thing related to limit point. I'll let you know. I think there was I read something. What will be the problem if we define in this way? Yeah, there will be some problem. I can't remember it right now. I'll let you know. Yeah. Now suppose x and y are two distinct points in R2 minus Q2. So obviously there are two distinct points in R2 as well. So clearly we can find two circles such that x is center of C1 and y is center of C2, and both are completely distinct. Be two circles in R2 such that x is the center of C1 and y is the center of C2. So basically we have x, we have C1, we have y, we have C2. Next we claim, now let's see. Uh, I claim that there exist uncountably many lines. There exist uncountably many straight lines joining x and points on C1 that are completely in the straight line is completely contained in R2 minus Q2. So basically we are saying this is C1, this is X. I'm saying that there exist uncountably many lines from X to this C1, points in C1, such that this complete line is lying in R2 minus Q2. And we have uncountably many such. Now suppose this is not possible. Let if possible, the claim is not true. So clearly we know that we can construct uncountably many lines from X to the points in C1, because yeah, clearly we have uncountably many options. So we have uncountably many lines. Now we are saying that there are uncountably, we cannot find uncountably many lines from X to C1 that are completely in R2 minus Q2. That means there are uncountably many lines which contains at least one point of Q2. That is why the problem is occurring. That means this implies there exist uncountably many lines from X to the point x to the points in C1, they which contains at least one point of Q2. There exist uncountably many distinct lines joining X and C1 such that they have they contain at least one point in Q2. That is why it was not contained completely in R2 minus Q2. Now, what does this tells? This tells us that Q2 has uncountably many points. But we all know that Q is countable, Q cross Q is again countable. So that gives us a contradiction. This implies Q2 has, because all the lines were distinct, Q2 has uncountably many points. But since Q is equal Q2, which is basically Q cross Q, is countable, this is not true. Hence, we get a contradiction. Therefore, by contradiction, our claim is true. Similarly, we can do for y as well. Therefore, there exist uncountably many lines in R2 minus Q2 joining x and points in C1 and y and points in C2. That means this is x, this is C1, this is somewhere y, and this is C2. We have uncountably many lines like this, which are completely in our space X. Now, if I extend these lines, so we can find uncountably many lines which will eventually intersect. So from here, we can see that there exist uncountably many lines in X, which is R2 minus Q2, such that they intersect and joins either X and C1 or Y and C2. So basically, if we can see that we get a path. In fact, we can find so many paths. Hence, we can find path joining X and Y. Now, since X and Y in X were arbitrary, therefore, X is path connected and hence connected.
Ma'am,
Hmm?
how can we guarantee that those lines will intersect. It is only seen on geometrically. How can you see it analytically?
So, basically, see, from X to C1, we can find lines in every almost every direction. Na? Similarly for Y. So, with that, basically, it comes from geometry only. I don't know how to write it properly.
And ma'am, how can we show that the extension of that line mm,
That will surely intersect.
that it doesn't contain any point of r square and irrational?
Oh, so basically, there might be some point here. That's in
Yes.
Q2. Mm. I think for that, maybe we can again go through the same arguments because we have uncountably many options. Now we can find at least. So basically, we need to find at least one.
Yes, and so that it can intersect with the line from another point also.
Mhm.
But how can we guarantee that?
It seems to me that this should happen because we have uncountably many options. But yeah, you are also right how to say that explicitly. Maybe we can go through the same argument because since we have uncountably many options, there also again, if that doesn't happen, that means there exists at least one point and all of them are distinct. We are seeing R2 minus Q2 as a subspace of R2. It may not work for other independently defined metric on R2 minus Q2, right? Such as discrete metric. Mayank, can you please explain what you're trying to say?
Ma'am, in this case, we are seeing R2 minus Q2 as a subspace of R2, right?
Hmm? Yeah.
So,
So,
okay. In My question is, in other cases, let's say we define other metric on R2 minus Q2, then it may not work.
yeah, here I think we are by default taking it to be the Euclidean metric.
Okay, ma'am.
Because wherever it's not specified, then we consider the Euclidean metric. Yeah, I'll surely think about it. Maybe we can go through, I think, a similar kind of approach because we have to get some contradiction starting with the uncountably many distinct options. You also try it. Maybe we can do with some similar kind of arguments.
Okay, ma'am. Mm,
Next, we will start with differential calculus. So suppose f is a function. Okay, show that if f from I to Rn is differentiable at some t naught, in I, then it is continuous at t. So whenever a function f is defined from some interval I in R to R, we know that every differentiable function is continuous. So basically, we'll be using that fact only because while defining f differentiability from I to Rn, so basically, if f is of the form f1, f2, fn, we have f dash is equal to f1 dash, f2 dash, fn dash. So we are mainly using the differentiability of the components function, and component functions are again from R to R. So that's what the main idea is for this problem. So suppose f from I to Rn is differentiable at some t naught in I. This implies f dash t naught, which by definition is f1 dash t naught and so on up to fn dash t naught is, sorry, this exists. This derivative exists. That means fi dash at t naught exists for every I 1 to n. That means each of fi is differentiable. Fi is differentiable for every I. And since fi is a real valued function, this implies fi is continuous for every I. And again, when a function I f is defined for the case of vector valued functions, it is said to be continuous if it is continuous component wise. This implies f, which is equal to f1, f2, fn is differentiable at t naught, at t naught, pi, pi is continuous at t naught for every. That's it. It's not for every. So this function differentiability implies continuity here as well. Next, the main difference between the vector valued function and real valued functions is the case where that the mean value theorem is not satisfied here. So we'll see how. Show that the mean value theorem is false for vector valued functions. By considering the example f t is equal to cos t sin t. So let's recall our mean value theorem. It states that for the case of real valued functions, if f from an interval I, which is a to b to r, is firstly continuous in close AB, then it should be differentiable in open interval AB. You know that then there exists some C in open AB such that f dash C is equal to fb minus fa by b minus a. Now let's start with the assumption that this function f satisfies the mean value theorem. Clearly, since its components are cos t and sin t, which are continuous and differentiable everywhere in R, this function is continuous and differentiable everywhere in R. So I can take I to be any arbitrary interval based on my choice. Solution. Suppose since sin t and cos t are continuous as well as differentiable on R, if mean value theorem was true for vector valued functions, then there exists some C in, let's start with some any arbitrary open interval AB, such that f dash C, this is equal to f of B minus f of A by B minus A. That is, now by we know that the way we define derivative of vector valued functions. So we have, since f t, this is equal to cos t sin t. This implies f dash t, this is equal to minus sin t cos t. So this implies minus sin c cos c, this is equal to, so I'll writing it directly. This is minus sin b plus sin a upon b minus a times, comma, cos b minus cos a by b minus a. Now, can you tell me some value of a and b for which I will end up getting contradiction here? Any idea?
If we take both AB to be same value,
Mhm. Mhm.
oh oh,
The mean value theorem is, I mean, we need an interval, na? I to be open interval A, B. So A and B should be distinct.
yes, yes, ma'am.
Taking A to be 0 and B to be 90 degree.
Yeah, that can work. So if we start with A equals to 0 and B equals to pi by 2, that means my interval I is 0 to pi by 2. So let's see what issue comes in this case. So this implies minus sin C cos C, this is equal to sin B. Sin pi by 2 is 1. So this is minus 1 plus sin A, sin 0 is 0 by pi by 2, comma, cos B, cos pi by 2 is 0, cos 1, cos 0 is 1. So this is pi by 2. So this is equal to minus 2 by pi and minus 2 by pi. So from here, we get sine c equals to, this is 2 by pi, and cos c, this is equal to minus 2 by pi. So can you tell me the problem here? How we will end up getting contradiction?
Squared sum should be 1.
Yeah. So this is 4 by pi square plus 4 by pi square. Obviously, that is not equal to 1. Also, this c should lie in the interval open AB, that means from 0 to pi by 2. And in first quadrant, this cos value is always positive. So by that also we'll get contradiction. So yeah, from here we can take both the cases. This implies 1 is equal to sine square c plus cos square c, which is 4 by pi square plus 4 by pi square, which is 8 by pi square. So obviously pi square is never equal to 8. So this is a contradiction also. And since c belongs to open 0 to pi by 2, this implies cos c should always be greater than 0. Again, we get a contradiction. Therefore, we get a contradiction. Hence, mean value theorem is false for vector valued functions.
Ma'am,
Hmm?
in proving the connectedness of R square by Q square, can we
Mhm.
use the same concept on arc, not using the circles, 45 degree arc angle,
Mhm.
and we increase the radius of arc to be greater than their distance between those 2 points x and y?
Mhm.
Then since that arc also contains uncountably many points, so there will be uncountably many rays also.
So
And
you're saying that if we have some point x here, some point y here, now you want to consider the arc.
join these 2 points with an straight line
Okay.
and
So
draw arc above that line of with 45 degree angle.
something like this. So basically
No,
we have
no, individually we take x as a center and y also as a center and draw two arcs.
from
Yes,
around x1,
yes,
something like this,
yes, yes, with 45 degree.
only till
Yes,
suppose this is 45-degree, suppose. And similarly for y.
yes.
Okay.
And we do the same procedure as we do in C1 and C2, that two circles with these two arcs.
Yeah, in this case also we'll be able to find uncountably many. But that's not necessary that these will intersect because
And
hmm,
and we can take the radius of arc as much as we want now. If we take the radius greater than the distance between x and y, then we can we say conformly that the two rays will intersect in r square minus
so you're
q
saying
square.
that you're taking the length of this arc to be greater than the distance between x and y.
Not length, the radius.
Radius. Okay.
Yes.
So if you take radius, so basically you'll go outside, na? This is x,
Yes.
this is y. You're taking radius to be larger than the distance. So something like this. Similarly for y.
Yes. Yes.
For y, you'll get something like this. Okay. Now,
Now we can find uncountably infinite rays joining x and the arc corresponding to it, and y and arc corresponding to y. And since those rays will not parallel, so they will intersect.
so you're saying that some path, something like this will be constructed.
Yes.
But this path will contain this arc, no? So we don't know whether this arc,
We,
okay, we
we
can consider that arc which was completely in R2 minus Q2.
let's suppose we don't consider that arc. We also draw su such arrays from x to the arc of that x, and then we
Something like this from
yes,
X to
yes, yes,
R.
yes,
So this and this will be the path. So the path will
yeah,
be something like this.
yes. And here we can we say that this totally completely line r square minus q square.
Because we are taking those lines only, no?
Yes, ma'am.
I'll check this. I think this can be done. I'll check this. Because yeah. Hmm. I think this is correct. I'll see it in detail if there is some issue. Otherwise, it seems fine to me.
Okay, ma'am.
Okay, so we do not have mean value theorem for the vector valued functions. Okay, so let's look at some functions, some multivariable functions. So I think that will be similar to what you must have done in multivariable calculus. So can we say we don't have mean value theorem in case of complex? Complex, if we consider it to be vector valued functions. Yeah, but in complex, the derivative is defined something, derivative is not exactly f dash, because if we have a complex function, um, so you are taking a function from R to C. R to C, f of x is equal to a complex value. f1x plus iota times f2x. I'll have to see this. Because the complex functions that we have studied are basically C to C. So I don't have much idea. If in this case, how derivative is defined, if we define f dash x to be f1 dash x plus iota f2 dash x, that in that case again we'll get similar kind of contradiction. So yeah, here C is considered as R2. It is isomorphic to R2. So in that case, we will not have mean value theorem. So the complex analysis, yeah, the complex analysis that we study in that case, our domain is also complex, no? Here we our domain is just the space R. Yeah. Sure. Let F from R2 to R be defined as fxy. This is equal to y is 0, y whenever x is non-zero, when x is 0. Prove that f is continuous at 0. So by 0 we mean the tuple 0, 0. And then we need to check, is it differentiable at 0 as well. So for continuity, we'll use the basic definition, the epsilon delta definition. Let's start with mod fxy minus f0, 0. So this is equal to mod y minus 0. Obviously, f0, 0, f at 0, 0 is 0. This happens when x is non-zero, and this is equal to 0 when x is 0. So this is basically mod y 0. I can clearly write it less than equal to mod y. Now this mod y can be written as under root y square, which is obviously less than equal to x square plus y square, because x square is positive. And this can be written as x minus 0 square plus y minus 0 square. So this is basically the Euclidean norm x minus y. Now, therefore, mod fxy minus f0, 0, this is less than equal to norm x minus y. This is strictly less than epsilon whenever norm x minus y is less than delta, which is equal to epsilon. So in this case, our delta is equal to epsilon. So therefore, by definition, for any epsilon positive, there exists a delta which is equal to epsilon positive, such that the distance between fxy and f at 0, 0 is less than epsilon whenever the distance between x and y is less than delta. Therefore, limit xy, oh sorry, this is the distance between xy minus 0, 0. Therefore, limit xy tending to 0, 0, fxy is equal to f at 0, 0. Hence, the function f is differentiable. Sorry, continuous. I hope this is clear how the function is continuous. So next for differentiability, we'll start with assuming, suppose f is differentiable at 0, 0. This implies in terms of directional derivatives, we know that f is differentiable if and only if limit norm h tending to 0 fx plus h minus fx minus h1 times the directional derivative in the direction of x, because this is the case of R2. So basically in Rn we get x1, x2, xn like that. So x, yeah, let me write it to be d, where d1 is the directional derivative in the direction of x into f at x by norm h. This is equal to 0, where h is h1, h2, d1 f x directional derivative of f in the direction of vector 1 comma 0 at x, and similarly we have d2f at x. So now if f is differentiable in our case, that means 0 is equal to limit norm h tending to 0 f 0 plus h minus f at 0 minus h1 d1 f at 0 minus h2 d2 f at 0 by h. Now let's evaluate d1 and d2 at f, d1 d2 d1 f and d2 f at 0. d1 f at 0, this is limit k tending to 0 f at k comma 0 minus 0 0 by 0 by k. So can you tell me what is the value of fk0? F at k comma 0. Here k is non-zero.
Zero na. We y
Look.
zero.
Huh. For x non-zero, the value is y. Here y, since here y is 0, so this is directly 0. Similarly, d2f at 0, this is limit k tending to 0, f 0 comma k. Now since x component is 0 in this case, so again this is 0. So this implies we have 0 is equal to limit norm h tending to 0 f at 0 plus h means h1 comma h2 minus f at 0 0 minus both the terms are 0 by norm h. So this is just limit norm h tending to 0 0. So for non-zero h1 h2, this is equal to h2 by norm h. So if I replace this norm by the Euclidean norm, this is limit h1 comma h2 tending to 0 0 h2 by norm h1 square plus h2 square. So can you evaluate this limit?
I mean, above f of 0k will be k, isn't it?
If at 0k, here the x component is 0. And see in the definition of the function, whenever x is 0, the value is 0.
Oh, yes.
No matter what the value at the second component is. Yeah. So can you evaluate this limit?
It will not exist, na?
How?
If we take h1 to be r cos theta and h2 to be r sin theta,
Hmm.
and then
If I take h1 to be r cos theta, h2 to be r sin theta, in that case, this will be limit.
r tending to 0,
Okay.
r sin theta upon
R.
r. R are good cancelled.
And now this limit does not exist because theta can take any value.
Yes.
Or you could see that along the path, h2 equals to m h1. In that case, also the limit will depend on this slope m. So this limit does not exist. But we were saying for differentiability, this should be equal to 0. This limit does not exist. Hence, we get a contradiction. Therefore, by contradiction, f is not differentiable. Therefore, this function was continuous but not differentiable. Next, I would like you to try this yourself. Um, Check the continuity and differentiability of the function x y to the power 6 by x to the power 4 plus y to the power 8 whenever xy is non-zero, 0, whenever xy is 0, 0. Check the continuity and differentiability of f at 0, 0. Try it. Yes, Mayank, you're right. Taking x equals to my square, yeah, the limit will depend on m. Therefore, the limit does not exist, hence the function is not continuous. And if a function is not continuous, we cannot talk about its differentiability. Along the path y is equal to mx square, we have f x mx square. This is equal to, so this is, sorry, x equals to m by square. No? We need to take x equals to m by square. We'll get my square y to the power 6 on my square to the power 4 plus y to the power 8. So this is my to the power 8 upon m power 4 y to the power 8 plus y to the power 8. So this is m by m power 4 plus 1. This implies limit x tending to 0 fx and x square. This is equal to m power 4 plus 1, which clearly depends on m. Therefore, limit xy tending to 0, 0 fxy does not exist. Hence, f is not continuous and differentiable at origin. So I hope this was clear. If you have any doubt in any of the questions we did today or earlier, please let me know. Otherwise, I'll stop here. I need to see problems after this. So in next class, for next class, I'll check your argument for Q2, R2 minus Q2. Otherwise, yeah, rest of the things were fine now. If you want anything else to be discussed in next class,
Yes, ma'am.
yes.
When we define the differentiability or differentiation of map from Rn to Rm,
Hmm.
that will be defined as a linear map.
That will be a linear transformation.
And yes,
Hmm.
and in when map is from C to C, that is complex to complex,
Okay.
then it is defined as usual as we define the differentiation from a real map from R
Yeah,
to R.
because we consider C to be the space. Here, Rn means we are taking the cross product of some spaces. No? There, C is taken to be space in itself. That is why we are getting the difference.
Can we not take C to be as R square?
If you consider C to be R square, then things will be different because there, see, iota also has some value that will make the difference.
Oh,
Because there we have a term iota also. Yeah, if you want to consider it just as a tuple, in that case, otherwise that will be function from R2 to R2. That will be something different.
thank you,
Okay.
ma'am.
So in next class, we'll continue with this differential calculus. Even I need to see the problems after this. So please let me know if you want some problem that you are facing difficulty. I'll start with that only.
Uh, Ma'am, in Stone-Weierstrass theorem,
Hmm.
I don't understand the term by separate in the third condition that's defined as separate points.
Strong Weierstrass theorem. Okay, I'll start with that in next class. Strong Weierstrass theorem. Okay, I'll start with explanation of that theorem. Then we'll continue with this differential calculus.
Okay, ma'am.
Hmm.
And ma'am, also limit superior and limit inferior of function sine n.
So was it some exercise problem?
Yes,
So
it was assignment problem.
assignment problem. So is the date gone?
Yes, yes,
Okay, so what was the problem? We have the sequence of functions. F n x is
sine n.
sine n x.
Oh, 1 minute.
Uh,
Sequence is sine n. Just
okay, we don't have sequence of functions. So
yes,
this is x n equals to sine n. So for this
yes.
sequence, you need to find the limit
Limits.
inferior and limit superior.
Yes.
Okay, I'll do that in next class.
And also any compact subset
So
of
basically, this is the direct, na? Limit superior and limit inferior are the supremum and infimum of the set of limit points.
yes.
So for sine n, what will be the set of limit points? Whole interval 0 to 1. You can see that because see, its graph is something like this, na? So eventually for each term, it will be repeating infinitely many times.
Actually,
So
variable is here natural number and discrete variable. So I don't understand how this
still,
go. The
still,
graph goes smooth.
the set of limit points will be close interval 0 to 1. You
Oh,
try to see this. I'll also see for a proper explanation if I can find. So basically, the idea is that the set of limit points is close interval 0 to 1, and since limit superior is the maximum, the supremum of the set of limit points, so it will be 1, and limit inferior will be 0. So I'll explain it properly in next class. Okay.
I mean, any compact subset of BCXR
Hmm.
is equicontinuous. How it will be equicontinuous?
So suppose A is a subset of
BC
BCXR. BCXR is the set of all bounded
bounded
linear
and
functions. And you're
and
saying
and
that
X
A is
X is
compact.
compact. X is given to be compact metric space.
X is a compact metric space. We need to show that this A will be compact.
This A will be equicontinuous.
But we need to show that
A is
okay, A is a
equicontinuous.
family of functions, so this family of functions is equicontinuous. I think that will come by the continuity of the functions. I'll look for its explanation and proper proof. I think it can be done. Okay, I'll do this. So we have already have 3 problems for next session. Then further we'll continue with the differential calculus. Okay then.
Okay, ma'am.
Okay.